Well, welcome, gentlemen and ladies. I guess the best way to just straight into here, I'll probably edit a little as I go to try and make up some time for Alex. What I want to talk to you about is a little about both the importance of thermal bridging and some of the work that we did for ASHRAE, because they recognize that thermal bridging is a big issue, but it's been a very, very hard thing to handle in standards like ASHRAE 90.1, so to a large extent it's been ignored. And when we start talking about the impacts of these thermal bridges, people suddenly realize, oh, we need to do something about it. Starting off, when we talk about thermal bridges, what we're talking about is heat holes. We're talking about highly conductive elements that are basically going through the insulation layers on buildings and taking the heat out. And if you've got a heat hole, it's kind of like putting a hole in a screen door. You can put a tighter mesh on, but the bugs are still going to get in. So that is the kind of the reason that we're dealing with this. Now, when I talk about this, I've been talking about these issues with architects and engineers and stuff like that for some time, and I try and make the point that there's a very big difference between complying with a standard and reality. To a large extent, I'm going to be talking about science and reality on this, and not necessarily what the words say about compliance with standards like ASHRAE. Clearly there's a relationship, but sometimes the relationship isn't very strong. This shows in the fact that with ASHRAE 90.1, they basically don't deal with thermal bridges because it was hard. And it is still a little bit hard, but I think we've made it easier. And in fact, they have this 5% exemption. If something is less than 5% of the envelope, yeah, you can kind of ignore it. That's not actually what ASHRAE says, but that's how everybody's interpreting it. And that means that if I put major pieces of steel running through my insulation layer, I can ignore it. Well, you may be for compliance, but not for reality. And we are trying to deal here with reality. There's been a bunch of talk with thermal bridges. Tomas was talking about thermal bridges and things like the psi factor. And maybe by the end of my presentation here, you will be sighing, but I'll try and explain that to you. Typically, historically, when we talked about dealing with heat load calculations, we had things like the parallel path and the isothermal plane calculation methods in ASHRAE, which kind of work if you're dealing with elements that are relatively non-conductive. Things like wood frame, those kind of methods work quite well. But when you start with steel and metal and concrete, you find that those things don't work because what you end up having to deal with is heat flow paths that are in 2 and 3 dimensions. Now we have software programs widely available, quite easy to use, things like Therm, which I think Tomas is going to be talking about a little bit next, which do 2-dimensional heat flow analysis to try and deal with this. But part of the challenges that we have right now is a lot of our details, particularly with steel and concrete, is when we're dealing with stuff that has 3-dimensional heat flow paths, and Therm doesn't deal with that very well. Now, just to show you some significance as a setup, this is the table 3 of ASHRAE 90.1 that talks about what the thermal value, what the U value or R value of steel stud walls assemblies is. And this is one for basically a 16-inch frame wall, fairly common, 3.5-inch. And basically what it's saying is if I put R13 into the stud space and I have sheathing inside and outside, it's saying I got R8. That's with all the air films and everything else that that wall assembly gives, I assume that I put R13 into steel studs, it's R8. And then they had that funny term, if you remember on the tables, continuous insulation, which nobody's actually defined very well what it means. But what it says, if I put continuous insulation out here of R8, that I'm saying that I'm going to get an R8 plus R8. I'm going to get an R16 wall, which happens to be the kind of wall that you would need for a steel stud wall in Zone 5. I know Zone 5. I come from Vancouver. It's Zone 5, so you'll see a lot of references to that. But one of the things is that when you start looking at stuff, that gets to be somewhat wrong when you start looking at stuff other than the steel studs. If you've a very simple analysis, if you just use concrete and tried to do a concrete slab with a wall above and below with an exposed slab edge, the typical way would be to do is a parallel path heat flow equation, which would drop you down if I put an R20 wall with a 6-inch slab. It's basically going to turn it down about an R8. due to the heat bridging through the slab and with the steel stud. So you see that it all is sort of cascading to the point that when we actually do real U value assessments or effective R value assessments of overall building assemblies, we're much less than those kind of numbers that the ASHRAE tables give. And a big part of it is because we live in a 3D world. The heat flow paths aren't parallel path. In fact, they're not even a two-dimensional heat flow path, they're a three-dimensional. So ASHRAE recognized that, so they threw some money at us and we got some work. Basically, and what we did was to sit down and try and calculate some of those common construction details, floor slabs, parapets, corners, windows, surrounds, base of wall details. Those kind of common assemblies that we have in construction, and we looked at masonry construction, we looked at steel stud, we looked at metal buildings, we looked at a variety of different assemblies. Ultimately what we did was we did 40 different complex details, many which included multiples of that, as this particular illustration here shows. We used three-dimensional finite element analysis. It's actually a Siemens program for those who are real geeks with a NX or a Maya solver. This happens to be the same software they do structural design on the space shuttle with, but it's just we're using it from the thermal perspective. We did a lot of calibration work against ISO standards and sets of data where there's lab data of known assemblies, where we compared to the known assemblies and came with a very close correlation. So we're very confident. There's always, when you're doing simulation, I'm the first one to question Nintendo engineering. But I'm actually very confident that we're in a very close range here in real life. We've done sufficient work to make us confident with that. We did 40 assemblies. These details are all published. You can get it from an ASHRAE report. It's a published report. You can buy it from ASHRAE. Or if you have your pen handy, at the end of my presentation, I have a link. We have a link, a little microsite on our company website. And we paid ASHRAE so we can distribute the report for free. So you can deal with ASHRAE or you can write fast, right, when we get to the end. Now we did a whole bunch of details. We did precast slabs. We were looking for the details, but interestingly enough, we weren't quite sure how we were going to analyze the data before we did all these details. And one of the interesting things is that once we got our heads screwed on right and we were doing the analysis, we learned a lot of stuff that's led us to believe we want to do a whole bunch more work, which we're actually looking at right now. So we did precast details, we did masonry details, we did steel stud details. We did not do wood details. Why? Because we don't think there's a real problem doing the calculations there, and we were optimizing where we were headed. I could even deal with that. Now, you heard the term psi value from Thomas. You're going to get a lot more psis as you're looking through your future life. Because one of the things is that one of the conceptual breakthroughs that we did when we were looking at all this stuff and trying to generalize the results, because nobody wants to computer model every building that they do, except perhaps the engineers who do computer modeling. So what I basically want to get across to you here is that you can think about the impact of thermal bridges in three kind of categories. There are ones where the thermal bridges are so widely distributed that you actually want to modify the U value to get an overall U value of a wall assembly or a roof assembly. Then there are thermal bridges where basically it's due to some linear assembly. Think of a slab edge, think of a corner, think of a parapet, where it is smarter to understand how much heat loss there is per linear element. And the Europeans have been doing this in standards for a while, and they call that psi. It's another Greek letter, and that scares people, but it's really just linear transmittance. So instead of based on the area, it's based on the line. And then if you go really smart in engineers, 1, 2, 3, well, I can even make it a point transmittance, and I can have something, and they have a term for that too. It's called chi. Right? Well, let's forget the Greek, and I'll use a linear point transmittance just in terms of those details. Now, the beauty of this is if you have a complex three-dimensional model that actually calculates heat loss and you're willing to use it, you can calculate, you can figure out some assembly, you can draw it up in 3D, you run it through the program, and you get a heat loss through that whole assembly. then I can do the same thing with the same type of system that doesn't have that element, in this case a slab. What's the difference? That's the heat loss due to the slab. Now, what we have typically done in North America is try to attribute that to some set area of the wall. Maybe it's a wall height or for 2 feet. That's been the way we've been thinking, to modify the U value. Well, the beauty of what they've been doing in Europe is they say, forget that, why use area? I will ascribe it to a line that has no area. So when I want to find heat loss in a wall assembly, what I basically do is I look at the U times the A, that's the stuff for the clear wall without that assembly. Then I do the sum of my psi values, or my linear transmittance values, but multiplied by the the number of square linear feet of that, that particular assembly. And then if I have anything I have to count, like maybe it's a structural connection that's coming out of a roof to carry or a structural connection out of a wall to carry a canopy, you just add them up. And once you add all that, you get the overall heat loss. And if you want to, you can actually divide that by the area, and you can have the U value to plug into your program. Or, more importantly, I strongly suggest that anybody who's doing heat loss calculations and takeoffs on buildings, they don't do that. They carry the number with the heat loss due to those linear elements, because you'll see how big they are. We'll throw a little bit more about that. So anyway, getting back, so if you guys grasp that concept of using the linear transmittance and the point transmittance as well as the UA, I have done my job here. I go home happy, right? Because that is a breakthrough that I think we have to make in North America. So the only reason I'm talking here is I'm becoming an apostle of psi, right? So, but what I do have is, with the ASHRAE report, one of the things we did is we have these 40 assemblies. This happens to be a data sheet from one of them. We've got numbers here, we've got information on temperatures, we've got information on U values, we've got information on the psi value and the chi value. Here is an example, is a system. This happens to be a precast sandwich panel, and when you look at it, you see that I am giving, in addition to the U value of the wall, we're also giving you what we expect the linear transmittance at the slab edge is, and the linear transmittance of the joint is, the connection between 2 panels. That means I can now figure out the overall U value dealing with those thermal bridges for any size of panel. I'm not generalizing. I can do it any way. The way we dealt with temperature is Thomas. He came up with a number, and he was using I think it was a theta or whatever. But we use the term in Canada, our temperature index. You probably, when you're dealing with windows, you're used to doing the condensation resistance factor. That's just the temperature index. It's dealing with the surface temperature. So we actually plotted stuff using temperature numbers, and then we gave temperature indexes of some of the critical surfaces. This is all in the report. I won't make you do any calculations. And for any of you who are the real geeks who have to do this, get the report and you could look at these numbers. And we're coming up with some stuff, and I have some sort of bite-sized pieces of information that I've got at my table over there. But here are some numbers that I've just plucked out of the results that I think are just good touchstones for you to learn from. One of the things that we're kind of doing a lot of is let me just flip here. A lot of the wall systems we are dealing with, we have to carry the cladding through the insulation. In other words, the structure's inside and we're carrying the cladding. So we have some kind of framework system that's doing that. And we do a lot of this in Vancouver. This is a standard wall type for a lot of the high-rises we deal with. And they'll have either steel stud, backup, or whatever. And then they're doing something. A lot of contractors just do vertical Z-girts or Z-girts. Z-girts for Canadians, Z-girts for you, right? So excuse the translation. And they can be run into vertical stuff, which is structurally very efficient, but thermally not so much. We can do it horizontally, or we can do it something that's horizontally and vertical with different layers of insulation to lengthen out and make tougher that three-dimensional heat flow path. Or we can do things like minimizing the amount of metal going through by using a clip system instead of using girts to go all the way through. Or we could spend money on things like night wall, which are these proprietary systems that we're coming up with. So we model a bunch of those. the systems that you're looking at here, all of these ones that were not proprietary, I've got the line here. What's really important is if you look at it, where was the, do we have the pointer? Is it here? I could do without it. I guess I will. But if you look at the number here, looking at the R20 insulation along the bottom, and that is the nominal R value of exterior insulation. So these are all on steel stud assemblies with no insulation in the cavity. These are all exterior insulation. You put R20 on, and if you look at something that is just vertical girts, you're ending up, you look at R20, if you just do straight continuous vertical girts, you're only actually getting about R11. Right? If you use the horizontal girts, you're getting a little bit more. You might be up to R13, R15, if we're dealing with horizontal and vertical with 2 layers of insulation. And then if you're getting, this line here happens to be a clip system where it had a 6-inch clip every 36 inches, right? And this, by the way, the red stars, that's the night wall system. And this is a fiberglass clip that you've probably never heard of down here, but it's a system that's, sort of a proprietary system that's in Vancouver. And the black line happens to be the line of what ASHRAE says you get with continuous insulation. Right? So, this is what you get meeting the requirements for compliance with continuous insulation, and here's what you're getting in reality. Right? There's a significant difference. And so get that in your head that continuous actually means very little metal through the insulation. You can probably get pretty closer if you're just using screws or fasteners, and there are ways of doing that. But if you're actually getting kind of a structural connection, you have some challenges. We do happen to do a lot of curtain wall and window wall, and this is one where we're getting a lot of misunderstandings by architects. This is the spandrel section of a curtain wall. It happens to be a very common stick-built curtain wall. I won't mention any names that start with K. But what there's a back pan with insulation in the back pan. And then what we did is, because one of the things is people know that they really suck thermally, is we're going to spray foam insulation on the inner face of the back pan to up the insulation. So the question is what do you get? Now here's the curve. Now the first thing that I want to get across to every architect who's looking at curtain wall, it says if I move from R5 insulation in the back pan to R25, how much of an improvement do I get? This is called the law of diminishing returns when you have big heat holes called a frame. You can add all the insulation you want in the back pan, and you're not going to improve your thermal values by very much. Now there are some ways that you could do this, some isolating back pans and stuff like that, so you're not dealing with the frames, but that raises condensation issues in its own right. And furthermore, as I said, in the model, we sprayed the inside of the back pan with 2 inches of spray foam, closed cell spray foam insulation, which is about R12. How much did I get? About R4. Right? So it did some good, but not by very much. And there are places, so we do this. We do spray the inside of back pans on some things to up the value. But why is that? That is because when you start thinking about it, in the vision section of the curtain wall, I've got the windows and I've got the frame, the exposed frame. That's sucking heat in, and then it's taking it down in the lateral path downwards to where the insulation is. Past the insulation. So I bypass the insulation with the frame, and there's no way around it. Right? So when I see buildings with 85, 90% glazed area, whether it's got back pans or not, and I hear that and I hear lead, I start to cringe. Because there's no way unless you're lying. Right? So that's kind of the point that I'd like to make. No, those are dealing with issues that relate to the area of the wall. We're talking about modifying the U value, if you will, the effective R value. I want to shift gears and start talking about some of these linear elements that we're talking about, the stuff that's handled by size. This is the dirty secret in Vancouver. If anybody's ever seen pictures of Vancouver, we have lots of buildings that are concrete. And they're interior insulated concrete. It's formed concrete. And I bet you, thinking about people who are talking about blast and stuff like this is the concrete bunker with interior insulation. I bet you there's a few running around in Army properties. Now, we did this number, so what we did is we modeled with the slabs and we modeled it without the slabs. And if you think back to what Joe was taking and the aqua and stuff like that, when you do this, you look at it. Now, sometimes somebody throws some numbers. So for some reality, an R10 wall has a U value of about 0.1. So if I show you a number that says the heat loss is 0.47, BTU per hour per linear foot, that's the same as having 4.7 feet of R10 wall, or a little over 7 feet of R15.6, which, back to what I said, that's what you basically required if you were in a zone 5. So if you have this condition where you've got a poured concrete building insulated on the inside, this happens to be 8-inch slab, 7.5 inch actually, because that's what we build in Vancouver to get the cover. That's like adding 6-7 feet of your wall. So you just raised your building in terms of its area. I mean, that's a fairly dramatic concept. So I can tell you that by what's the modification of the U value, but if I told you you just raised the building, your wall area by 5 feet, it's a thing. Now, another interesting thing, just so that you get some perspective of what the change is. Here's a very simple wall where we just took our exterior insulation and ran it past the edge. This one happens to be different. It's a steel construction. And we all know that that isn't a particularly good detail, the way that beam is handled. But I went from, this is 0.09, so this is less than a foot of my R10 wall. Right? So this is not fancy. This is, I would suggest to you, the minimum that you should be aiming at type of thing for a number, for a psi value. Right? And it's basically less than 20% of, it's less than 20% of what we've been building in Vancouver. Another interesting thing is everybody talks about these balconies and everything else. Well, we did a fair amount of analysis for that because we have a lot of these balconies because most of the work we do is actually high-rise residential. And we also have eyebrows, these little things that stick out, which were thought to be a good idea for rainwater protection and shielding. And then a simple exposed edge slab concrete building. There's no significant difference in the heat loss between those. It's so bad that the insulating value of the concrete on the bigger ones makes up for the difference in the fin effect. Right? And that is because you're already connected, your slab's connected to your exterior wall. So you've already got your fin, so you add a little bit more fin, it makes no real difference. So they're all the same. So don't necessarily blame all those ugly balconies if you've got an exposed slab edge. If you haven't insulated the outside edge of your frame, you're already messed up. So here's just a few other numbers very quickly going down. Here is an exterior insulated block wall assembly on a balcony, quite common in residential, high-rise residential construction. Okay, we're down to 3.4 feet, right? If we do a shelf angle that's bolted to the slab edge or cast into the slab edge, 2.7 feet. If we put knife edges in and hang the shelf angle off and put the insulation in behind it, right? We're down to less than 2 feet. Makes quite a big difference when you consider this. It's actually cheaper to do this than to put the big shelf angle to support the masonry weight, because you can use a smaller shelf angle. And I love Germans. This particular side, this is for a product. It's a German product. It's a commercially available product that is an insulating structural assembly that you can do you put into a slab edge and it will take the moment loads of the slab. Right? It's over-engineered, German, and expensive. Right? But it works, and it works very well, and it's now being sold in North America because I can't get the guy off my doorstep. Right? Because this is a product whose time has come in terms of when you're dealing with residential construction because it's a way of isolating the balconies. Virtually every building, every balcony, etc., in Germany or Switzerland probably has some version of this assembly now because they have specific requirements for psi values, etc., for these things. Concrete walls. What's the difference between a concrete shear wall and a slab? Right? Orientation. Right? I don't care what your orientation is. But the interesting thing is there's a subtle difference between these two. This one here, we've just brought the insulation in, and here we've brought the insulation and then brought it in 2 feet into the wall, just the length, basically next to the heat flow path. And it makes a difference, but not as high as much maybe one wants, right? But that is one way of isolating things. We did a whole bunch. We've got a bunch of different parapets. I just thought I'd throw one up for use of steel, composite, metal stud concrete, steel pan concrete composite assembly. You notice there's no insulation on the inside of the steel stud wall. That's our point too. So that's like having 2 extra feet, right, on the assembly. And we did some stuff like, say, here is an HSS embedded in the wall so that we can hang an HSS, welded on HSS assembly that we can carry, a canopy or something, right? So we have these numbers. I've got some stuff at my desk. I have a few things, some of the stuff that I've drawn slides from, in sort of bite-sized pieces that we've given to architects and the like. Or you can get the ASHRAE report. I also actually have a copy of the appendix there that has all the details that we looked at. If anybody just wanted to flip and see what details were there, they can come over and just flip it through, and then they can go order it. We did a lot of work in looking at things to do the significance of this. I'm not sure. This is just a dummy building, 10 stories high, 20% glazing ratio. And we got obviously slabs and stuff like that. We looked at 2 different things that comply with the 2007 version of ASHRAE in Vancouver's climate. One was with interior insulated mass wall, and the other was basically a steel stud wall with exterior insulation. And we basically did we did the thermal analysis of that. And the interesting thing about that is when you look at it, the numbers that I want to point out to is the concrete building has almost twice the heating energy use. We did this based on, this is not our value, this is heating energy use, right? Is almost twice that of the exterior, of the exterior insulated assembly. Even though the exterior insulated assembly is not a very good assembly in terms of, because it's got all that thermal bridging inside it, right? And almost 40% of that was going for the slab edges. We were very surprised at how significant the slab edge effects are, right? And I'm not new at this game, and I was surprised. And we thought we were going to get R11 with the mass wall. We got R7. We thought we were going to get R15.6 with the steel stud assembly, and we got R11. This was another big surprise. The Metal Building Association asked us to model insulated metal panels because they're so good. They just wanted to prove how good they were, and they were. But they also said that at every through-wall flashing or all the windows, you have to put a metal flashing that went past the insulation and attached to the metal frame behind the insulated metal panel. So that's a thermal bridge. Every flashing is a thermal bridge, right? And that basically kicked it from stuff that was basically up in R21 to R8. Now that's a big deal, but the good news is it's very easy to fix. And certainly insulated metal panel, when you've got no structural, the structural assembly that holds the cladding on is fully insulated, right? There's no thermal bridges through the assembly. Makes them a very good choice for high efficiency. Now there's a couple of things when looking at overall heat loss and stuff like this. While I think it's important that we understand the impacts of thermal bridges, we kind of have to make sure we understand the importance of stuff. This is some modeling that we did to look at how does effective thermal resistance affect overall heat loss in a building. Actually, overall energy, heating energy use. And you find that there's a law of diminishing returns. If you can actually get walls up to the effective R15, R20, you've got a building, you start adding more insulation, you don't gain it very fast. And when you do that, what you end up finding is, because a lot of the good thermal details with thermal bridges actually are putting insulation on the outside of it, that as you get to the better walls, you find the difference between having a good or a bad detail at things like window surrounds and slab edges and stuff like that becomes a much, much bigger deal in the overall performance of the wall assembly. So as you start thinking about removing thermal bridges, you find you've almost multiplied the effect. It's a synergistic effect of getting good effective R values and low energy use. That said, looking at the future, we've got products coming out. I mentioned the Isocorp thing on the bottom corner, the night wall you can go look at over there. We've got the insulated metal panels. There are products out there. We're not necessarily always having to do it by, figuring out as we're going along. There are some pretty good products that are out there that help us a lot. And this is one thing I want to leave with all the architects. It's not necessarily related to what I'm talking about, but we took a LEED compliant building and then we modeled different heat loss, the heating energy use, so total energy use, by varying different things to show the sensitivity of stuff. So the purple line, right, I think it is the overall RS, we start looking at the wall values. The overall, this line, and it's kind of buried in here, and you can almost not see it, but notice what the slope is. Now, that blue line is window-wall ratio. One of the things that bothers me, so in other words, if somebody decides that they want to have a high window-wall ratio, somehow or other we have to, from all of these other things, we have to suck back gains to get down there. And I'm getting very frustrated with architects that say, I want 80% glazing, facing north and west, because that's the views, and the mountains to the north in Vancouver, the views, the ocean to the west. So I want 80% glazing on those faces, and somehow or other you're supposed to figure out how we're going to comply with ASHRAE 90.1 or any of your energy standards. Right? So a bunch of things that tie in what Thomas was saying is we've got things here where we're talking about the psi value being a very important concept to understand, right? And then secondly, that in talking about this, the window surrounds, the slab edge details, these are details that you really have to look at, because if you're taking the tables from ASHRAE or doing this without considering that, you're way off on reality regardless of what you are on compliance. And very quickly, yeah.
I'm Chris Draper, and I work with Mark Lawton at Seattle, and Melinda here is out of Atlanta. I just wanted to mention something before Mark ran out of time in terms of some of the things that we're seeing here, down here in the U.S., where this is being applied very quickly. We're getting a lot of requests recently from GSA, as well as some of the architects that do work for the U.S. Army Corps of Engineers, where they're trying to comply with the new energy efficiency requirements that we know that you're all under. And what this has really helped us do is actually isolate the conditions where we need focus. So with all of these details, we don't have to model every building, but we really are able to sort of say, okay, here's the building design, and here's where the problem areas are. Let's focus on that, and let's figure out how to minimize the thermal bridging at those locations. And so we've kind of worked with some of the architects that do U.S. Army Corps of Engineers work down here on this side of the border as well. So.
Thanks, Chris. So anyway, that link at the bottom is the link to your free copy of the ASHRAE report if you want it. There's actually a bunch of other publications, like the Metal Panel Association to let us publish it. So you can actually, a bunch of the stuff that I've got here in terms of literature is there, right? Or you can just go to ASHRAE.org. If you basically search 1365 RP, which was the research project number, I'm sure you can buy it there. I have no idea what they charge because I refuse to pay them. Okay?